Hi, welcome to Chapter 7. In Part 1 of this lecture, we'll be dealing with rotational kinematics. Chapter 7 is split up into 4 parts. This first part will deal with rotational kinematics. Part 2 will deal with torque. Part 3 covers center of gravity and moment of inertia. And Part 4 is on rotational dynamics. In Chapter 7, we're dealing with the rotational motion of a rigid body. So a rigid body is an object whose size and shape do not change as it moves. So this example here, we see a solid disk rotating about this axle here. This is an example of a rigid body that's rotating. So the basic properties of this type of motion are that different points on the rotating rigid body have different speeds. So the farther away from the axis we are, the faster that part of the rigid body is going to be moving because it's covering more distance in the same amount of time. For a point close to the axle, it's still turning around like this, but it's covering less distance, so it has less speed. Every point on a rotating rigid body rotates by the same angle, theta. So as this object rotates, the angular displacement of the rotation is the same everywhere because the angle just tells you how much the object turns. And every point also has the same angular velocity, omega. Remember that omega is the number of radians per second. So it's the rate of change of the displacement. So again, this doesn't matter where we are on the object. The entire object is described by one angular velocity called omega. Let's look at a little demonstration here. Suppose we have this bicycle wheel and we start pushing on it with our hands. Notice what happens to it. It starts to speed up. So this is an example of a non-uniform circular motion. Remember in uniform circular motion, the speed of rotation was constant, but here the object is speeding up. So this is called angular acceleration. Angular acceleration is given the Greek letter alpha. Now this is to distinguish it from the letter A, which refers to linear or translational acceleration that we studied earlier in this course. So alpha, or angular acceleration, is defined as the change in angular velocity divided by the amount of time it takes to do that. So we have alpha is equal to delta omega, remember omega is angular velocity, divided by the time it takes. Just one clarification here right from the start. Angular acceleration is not the same thing as centripetal acceleration, and we'll distinguish between these two in a couple slides. So angular acceleration, alpha, can be positive or negative, just like regular acceleration could be positive or negative. So in the case that we just saw, where we had the wheel spinning counterclockwise, remember that counterclockwise is our positive direction because the angle theta is increasing with time. So if an object like this wheel is going in the counterclockwise direction and it's speeding up, all right, that means the alpha value is positive. Okay, the angular acceleration is greater than 0. Now, on the other hand, let's say that the counterclockwise rotation starts fast like this, and then it slows down with time. So this is an example of, you can think of this as angular deceleration, or alpha is less than 0. This is a negative angular acceleration. There's another way to get negative angular acceleration, alpha less than 0, and that is if the object is rotating in the clockwise direction. Remember that this is, by definition, this is a negative direction. So if an object like this wheel is speeding up in its rotation in a clockwise direction, that's another example of a negative angular acceleration. When we deal with the rotation of a solid object, there are really 3 different types of acceleration that are involved. So let's try to clarify between the 3 of these. So the first one, this is the first one we learned about in the last couple of chapters. This is centripetal acceleration. Remember that centripetal acceleration, A sub c, where the c is for centripetal, means center seeking, and we can calculate centripetal acceleration by v squared over r, or r times omega squared. What centripetal acceleration really means is the velocity of the object that's moving in a circle here doesn't have to be changing its speed, but its direction is changing. So centripetal acceleration basically changes the direction of the velocity vector. And remember, it always points towards the center of the circle. What we just learned about down here was angular acceleration, alpha. And that is when we have a change in rotational speed of the object. Okay, and alpha is defined as delta omega over delta t. Now, if we think about an object on the outside of this, let's say this is a wheel, and we think about this object and the wheel is accelerating, right? It's going faster and faster. Well, then the speed of this object is also accelerating. It's getting larger and larger. So this is what's called tangential acceleration. Tangential acceleration is the acceleration of a point on the edge of a rotating object. And notice it points tangential, or at a tangent to the circle in the same direction that the velocity is increasing by. So that's completely different, of course, than the centripetal acceleration, which points towards the center of the circle. By the way, tangential acceleration is related to angular acceleration, alpha, by the equation a sub t is equal to r alpha. This next slide here is a bit busy, but it's a nice summary of all of the equations of kinematics that we're going to work with. So again, there's sort of bad news and good news here. The bad news is for rotational motion, we've got a whole bunch of new equations over here that we're going to be using. Okay, so obviously that, at first glance, that's like, oh no, here we go again, right? The good news is all of these equations are just the same ones that we used in the first few chapters of this course. The only difference is that we replace the position variable, either x or s, we replace it with the angular position, theta. We replace regular velocity with omega, which is the angular velocity, and we replace regular acceleration, or linear translational acceleration, we replace that with an alpha. Okay, so let's look at some of these formulas and you'll see what I mean. So for position, when we're talking about an object just moving in a straight line, we can use either the variable x, or we can use s if it's the motion along a circle. But for rotational motion, we are going to deal with the angular position, right? What angle along the circle it is. And those relations, those two quantities, s and theta, are related by s, the arc length, equals r theta. For a displacement, we saw that a displacement is equal to final position minus initial position. Well, the same thing goes for rotational motion. All we do is replace the s here with theta. So wherever we see an s over here, we put a theta in over here. So a rotational displacement is just the final angle minus the initial angle. For velocity, velocity is the change in distance or position, which is a displacement, delta s, divided by the time interval. So again, we replace v with omega, we replace s with theta, and here is our definition of angular velocity. All right, it's the angular displacement divided by time. And those quantities are related by v is equal to r omega. For acceleration, we know from earlier in the course that acceleration is the change in velocity divided by time. Well, now we just take the a, replace it with alpha, we take the v, replace it with omega, and here is our definition for rotational motion. This is angular acceleration, is the rate of change of the angular velocity. So it's delta omega over delta t, and a and alpha are also related by a simple relationship here. A sub t is equal to r times alpha. Now, for kinematics, for linear motion, for an object moving in a straight line, We learned a bunch of equations earlier, like the final velocity is equal to initial velocity plus acceleration times time. Well, we can take this same equation and just replace the v's with omegas and replace a with alpha. Okay, so again, we're using these replacements up here, and we get the equivalent relationship for rotational motion. The final angular velocity, omega final, is equal to the initial angular velocity plus alpha times time. We saw for a displacement is given by the initial velocity times time plus 1/2 at squared. Well, again, just by changing these variables, replace s with theta, replace v with omega, and replace a with alpha, and we get the same equation as it corresponds to rotational motion. And then the last one here is one that's often useful. It's the one without time in it. The final velocity squared is equal to initial velocity squared plus 2a times the displacement, delta s. Again, replace v's with omegas, replace a with alpha, and replace s or x, the displacement, with theta. And so here is here's the corresponding equation that we can use for rotational motion. So this is a handy chart to have at the ready there when we're doing homework or working on quizzes and so forth, because this has got all the equations that we're going to need. So let's go ahead and start doing some examples and problems to practice this. So here's our first example on rotational kinematics. A frisbee has a diameter of 15 centimeters. While flying, it rotates at 1 radian every 0.2 seconds. What is its angular velocity? So here in this little animation here, we can see our frisbee sort of spinning. We're showing it here in slow motion, though. It's spinning much faster than this. But what we're going to do here is we're going to use the equation for omega. Omega is the angular displacement divided by time. And we know that this frisbee turns 1 radian every 0.02 seconds. So 1 divided by 0.02 is 50. And you can see our units are radians per second. So what this says here is this frisbee is rotating 50 radians every second. Okay, remember the radian, of course, is a unit of angle. Okay, so the second one, what is the speed of the rim of the frisbee? In other words, how fast is something going on the outside edge of this frisbee? So here we're going to use the relationship, if you look back on that previous slide, velocity is equal to r times angular velocity. So the radius is 0.15 meters, right, 15 centimeters, and we just figured out omega was 50. So this multiplied together, this gives us 7.5 meters per second. That's how fast something is moving on the outer rim of the frisbee. How many revolutions does the frisbee make during a 5-second flight? Well, first let's find out what the angular displacement is of the frisbee. In other words, how many radians does this frisbee actually rotate in 5 seconds? So we know that omega is equal to the angular displacement divided by time. So the angular displacement, delta theta, is just equal to omega times the time. So omega, remember, is 50 radians per second, and the time is 5 seconds. So 50 times 5 is 250, and you can see the units here, the seconds cancel, leaving just radians. So this frisbee rotates 250 radians during the 5 seconds. Now, we're asked to figure out how many revolutions is that. Well, remember, so what we have to do basically is convert the radians to revolutions. So we multiply 250 radians by this conversion factor. Remember that 1 revolution is equal to 2 pi radians, okay? Just like it's equal to 360 degrees, but there are 2 pi radians in a full circle. So we have 250 divided by 2 pi, and that turns out to be 39.8, so about 40 revolutions. Here's a second example of rotational kinematics. A ball starts at rest and rolls down a hill with an angular acceleration of 3 radians per second squared. What is the ball's angular velocity after 10 seconds? So we can look back at all those equations for rotational kinematics, and find the one that has final velocity in it. Remember that, there are a couple equations that we could use there, but this one works by, the best because we know the time, 10 seconds, and we also know alpha. We're given alpha right here. It's 3 radians per second squared. Also, the ball is starting at rest, so the initial omega is 0. So this is our equation here. The final omega is equal to alpha times time. So we have 3 radians per second squared times 10 seconds, and that gives us our answer of 30 radians per second. There's the final speed. How many revolutions did the ball make during those 10 seconds? Well, there's actually 2 ways we can solve this. We can use the distance formula. Remember, for an object starting at rest, we have d equals 1/2 at squared. But now we're working with rotation. So instead of distance, we're talking about how many radians. Delta theta is equal to 1/2 alpha t squared. So we have 1/2 times 3 times 10 squared, and we get 150 radians. Okay, remember, we knew alpha was given up here, and the time is 10 seconds. So this comes out to be 150 radians. Now we have to convert that to revolutions. Just like in the last problem, all we do is multiply this by 1 revolution per 2 pi radians. So we have 150 divided by 2 pi, which gives us 23.9 revolutions. Now the other way to solve this problem is perfectly fine as well. We can use this equation for final omega, and we can solve this for the delta theta, the angular displacement. All right, so doing a little bit of algebra here, delta theta is equal to omega final squared minus omega initial squared divided by 2 alpha. And we know that our final omega is 30. So this is 30 squared right here. Omega initial is 0 because it starts at rest. So we have 30 squared divided by 2 times, remember alpha is 3, and that gives us the same number of radians, 150 radians that we got here. And then of course we can convert that to revolutions as we did above. Let's look at a couple more examples. In these 2 examples, we're going to be calculating the angular acceleration of an object. So in the first one, it says a wheel's angular velocity increases from 12 radians per second to 32 radians per second in 4 seconds. Calculate the wheel's angular acceleration. So this is just a straightforward application of the formula for angular acceleration. Alpha is equal to the change in omega divided by time. So that, remember, the change in omega is omega final minus omega initial. So that's 32 radians per second minus 12 radians per second, and it took 4 seconds to do this. All right, this was all given to us in the problem. So 32 minus 12 is 20, and we see that 20 divided by 4 gives us our answer of 5, and the units, you can see that comes from the units here. The units are radians per second squared. This second example here on this page, it says a propeller's angular velocity decreases from 120 radians per second to 70 radians per second while making 20 revolutions. What is the propeller's angular acceleration? So this one, notice that we're not given any time here. Up here, we were given time, so we can use this simple just definition of alpha, right? But if we don't know what the time is, we're going to use this equation here. This is the equation without time. This is a final omega squared minus initial omega squared plus 2 alpha delta theta, okay? So now what we're going to do here is we're trying to figure out what alpha is, the angular acceleration. So the first thing, let's do some algebra. Let's solve this equation for alpha right here, right? So we move, this term, move it to the left side and divide by 2 times delta theta, and we get this result here. Alpha is equal to omega final squared minus omega initial squared over 2 delta theta. Now, what do? We know these 2 numbers, okay? They're given to us, but all we know is that it made 20 revolutions. So we need to figure out what is 20 revolutions in terms of radians, because remember, delta theta is in radians. So delta theta is equal to 20 revolutions times 2 pi radians per revolution. All right, so what we're doing is we're converting revolutions to radians by multiplying by 2 pi. Okay, so 20 times 2 pi turns out to be 126 radians. So that's the number we stick in for delta theta down here. And then if you do the rest of the math, you'll come up with a negative answer. It's negative 37.7 radians per second squared. Now, what does this mean? Well, a negative alpha, a negative angular acceleration in this context just means that the propeller is slowing down. It's not speeding up, right? It went from 120 radians per second to 70 radians per second. So its acceleration is negative. Here's another example of rotational kinematics. This one involves a drag racing car may obtain speeds up to 300 miles per hour in just 5 seconds. During this time, the wheels go from complete rest to 75 revolutions per second. So this is a three-part problem here. What is the final angular velocity of the wheels? Calculate the angular acceleration of the wheels, and how many total revolutions does each wheel make during the 5-second race? So let's go ahead and look at the solution to this problem. Okay, the first part, part A, said what is the final angular velocity of the wheels? Well, we were told that the wheels go from 0 to 75 revolutions per second, all right? And so all we have to do here is convert revolutions per second to radians per second. So how do we do that? Well, again, we're going to multiply. Remember, each revolution is 2 pi radians. So if we multiply this by 2 pi rad per revolution, the revolutions cancel, and we end up with 75 times 2 pi, which is 471, and the units that remain are radians per second. So there's our final angular velocity. Part B asked, what is the angular acceleration of the wheel? Well, the wheel, remember, is going from 0 at rest to this final velocity, 471 radians per second. So alpha, angular acceleration, is just the change in omega divided by the time. So the change is 471 radians per second, right? That's our omega final, which is 471 minus 0. And it took 5 seconds to do that. So 471 divided by 5 is 94.2. And you can see here the units are radians per second, or radians per second squared. Part C asked, how many total revolutions does the wheel make during this 5-second race? So there are 2 ways to do this problem. And you know, again, we often see this in physics, that there's more than one way to solve the problem. So the first method, we can use this displacement formula here, that the angular displacement, delta theta, is equal to the initial angular speed, which is 0, by the way, so that's nice. Cancel out this term. And we get 1/2 alpha t squared. So alpha, we just found out, was 94.2. And the time, remember, is 5 seconds for the race, and we have to square that. Don't forget the square. So the number of radians is equal to 1/2 times 94.2 times 25, and that's 1,178 radians, okay? But now we have to convert that to revolutions. So the number of revolutions is equal to the number of radians, 1,178, times 1 revolution per 2 pi radians. So on our calculator, we just do 1178 divided by 2 pi, and that will give you the answer of 187 revolutions. The second method, which is equally good here, is the equation without time. So this is the final velocity, final omega squared equals initial omega squared plus 2 alpha delta theta. So again, initial velocity here is 0. So our final our final omega is equal to 2 alpha delta theta. We can solve this for the displacement delta theta. So it's equal to the final omega squared divided by 2 alpha. Now, omega final, remember we found that in part A. It's 471. So we square that, we divide it by 2 times, and remember alpha, we found that, let's see, where did we find alpha? Right here in part B, 94.2 radians per second squared. So this turns out to give us the same delta theta of 1,171 radians And then, of course, we would have to convert that to revolutions, the same as we did right here, to get the same answer of 187 revolutions of the wheel. So here is our last example in this part of the lecture. And this is another multi-part problem. This problem has 4 parts, so it'll give us a chance to use several of the equations that we're learning about in this part of the chapter. So in this example, a fan blade rotates at 300 RPMs. When it is turned off, the blade slows down and makes 22 complete rotations before stopping. All right, so what do we know about this fan? Oh, and also in the diagram here, we're shown that the fan blade has a radius of 20 centimeters, okay? So here's kind of a picture of what's happening. This fan starts out spinning fast at 300 RPMs, and it's slowing down to a stop, right? We turn off the switch, and its angular momentum just keeps it spinning until it finally comes to rest. And we know that it makes 22 complete rotations. So let's answer these 4 questions. What is the fan's initial angular velocity while running? Well, we're told that it's rotating at 300 RPMs. So we need to convert that to radians per second. So our initial velocity, our initial omega, is 300 revolutions per minute. Now let's convert minutes to seconds. So we multiply by 1 minute per 60 seconds. And then we have to convert revolutions to radians. So we multiply by 2 pi radians per revolution. So here we're doing, multiple unit conversions. We're going from RPMs to radians per second. All right, and we have to do that in 2 steps here. So we have a bunch of numbers here. We have 300. We have to divide by 60, and we have to multiply by 2 pi, and that will give you 31.4 radians per second. Question number 2, what is the angular displacement of the fan after it is turned off? So in other words, while this fan is coming to a stop like this, how many radians does it rotate before it actually comes to rest? So delta theta here, remember we're told that it turns 22 times. So, most of the work is done for us. We just have to convert that to radians. So 22 revolutions, we just multiply that by 2 pi radians per revolution. So 22 times 2 pi is 44 pi, or 138.2 radians. There's our angular displacement. Part 3, what is the angular acceleration of the blades? So notice we don't have any time here given to us yet. We're going to actually figure that out in the next question. But at this point of the problem, we don't know how long it took for this thing to come to a stop. What we do know is how many radians, what the angular displacement of the fan blades are. And we also know what the initial velocity is here, omega sub I, okay? And, of course, we know the final velocity of the fan blade. As it slows down, remember, it's coming to a stop right here. So our final velocity is 0. So we're going to use this equation right here, the one without the time in it. So 0 is equal to our initial omega is 31.4. We learned that in part A, plus 2 alpha, let's see, times 138.2. And so what are we trying to solve for here? We're trying to solve for alpha, right, the angular acceleration. So we just have to do a little algebra now. I can square this number, 31.4 squared, and get 986. Let's move that to the other side of the equation, so we pick up a minus sign. And then we can divide by 2 and divide by 138.2. And here's our final expression for alpha. And when you do the math on your calculator, alpha ends up being negative 3.57 radians per second squared. So notice we picked up, this minus sign here when we did the algebra, and that minus sign carries here in our answer. So again, think about, what does a minus sign mean for an acceleration? Well, that means in this case that the object is slowing down. So it's decelerating, right? It's not speeding up, it's slowing down. All right, our last question of this part of the lecture. How long does it take the blades to come to a complete stop? So now we're going to solve for time. There are 2 ways to do this. The first way is by far the easiest way. We can use the definition of alpha, angular acceleration, is equal to the change in omega divided by time. So just solve this for delta t. The time is equal to delta omega over alpha. Now, what is delta omega? Well, that's omega final minus omega initial. The omega final is 0, right? It comes to a stop when it's done. And omega initial is this number up here, 31.4. And then alpha down here, remember, was we just solved for that negative 3.57. So what happens is this minus sign here at the top cancels this minus sign on the bottom. And so we end up with 31.4 divided by 3.57, which is 8.8 seconds. The second method, by the way, which would be considerably more algebra and work, is to use the quadratic formula to solve this equation here for time. This is the position formula. And you know all these numbers in here. You know delta theta, you know omega initial, and you know alpha. So you can plug those in there and plug it into the quadratic formula. But this is a bit more work, so it's certainly best to use this method shown here. Okay, so that is our talk, our lecture on rotational kinematics. Let's move on to part 2 of this lecture next.